Hey everyone, thanks for coming. You had a choice to be in two other rooms and you chose this one. I really appreciate that. And also thanks to the organizers for the opportunity to speak here. It's actually genuinely a privilege. So yeah, thank you. So yeah, I'm Jonny. I'm a data scientist at Deliveroo and I work in the merchandising algorithms team. So today I'm going to be talking to you a bit about what we do. And if you've looked at the title, you can probably guess that it's something to do with ranking of restaurants. So, a little more detail what I'll talk to you about. So I'm going to introduce Deliveroo for those of you that don't really know what Deliveroo is and introduce why we've started this merchandising algorithms team. And then I want to spend some time talking about our approach to ranking, and how it works, how we frame the problem, the modeling strategies that we're using. Then I want to talk a bit about the tools. So we have to not only build models, but we have to deploy this and serve these recommendations. So how have we done that? What tools have we chosen in the processes? And then finally, I want to finish off with a section on the lessons that we've learned. You know, we've deployed a few models, run a few experiments, and we've made some mistakes. And I want you all to learn from these. So yeah, and that's basically it. That's what I want to go through. So here's an introduction. So for those that don't know what Deliveroo is, you can think of it as a platform that tries to connect consumers to local restaurants around them. And that's through via an app where you can look for restaurants and you can order, and then we deliver. We have a fleet of riders and a rider will go pick up the order. So for example, if you want to go and order from Wagamama's doesn't have their own delivery fleet. So you'd have to go to the restaurant, order, and eat there. But Deliveroo allows you to actually order and enjoy the food from the comfort of your own home. So you'll go to the app, you can scroll through, find Wagamama's, click, order, and we'll send a rider off to the restaurant, pick up your food, and then they'll deliver that to your door. So that's the idea. And you can probably tell from the slide that it's a three-sided marketplace. We have tens of thousands of restaurants and riders and even more consumers in over 300 cities in 14 countries. So it's a big operation, a huge network. So if I'm a consumer and I want to go and order from the app, this is what I might be presented with. So on the left is what you might see on an app, and on the right you've got the web. And basically you've got a list of restaurants. And what we assume, our hypothesis is that depending on the order of the restaurants that you see, a consumer might behave differently, right? You may or may not order depending on what you see in that list. So enter the merchandising algorithms team, right? We start with an initial goal and we say, why don't we try and present the restaurants that are most relevant to the consumer first, right? Because we believe that that is a thing that's going to be best for that consumer, and they might want to purchase more. So that's an introduction to Deliveroo and the team and what we're trying to do. And so now I want to spend some time talking about our approach to ranking these restaurants. So I've already mentioned the objective. Given a list of restaurants, the user opens an app, there's a set of local restaurants, right? Given that, how can we rank them optimally? And optimal can mean many different things, and in our case, we want to say that it's relevant to the user, all right? So the question is, how do we quantify this? It's all right having an objective, but can I look at some numbers that will help me understand whether we're actually achieving the objective of showing the most relevant restaurants to users? So two of the metrics that we look at is order volume. Are we getting more orders in total over a period of time? And the other one is this session level conversion. And you can think of that as of the total number of sessions. So if a user goes on the app, of the total number of times that someone goes onto the app, what proportion of those actually result in the consumer actually ordering? That's the way you can think of it. So the idea is that these two metrics, the order volume and the session level conversion, if we increase those, that's likely due to the fact that we're improving the relevance of the restaurants that we're ranking. Right? That's the idea. So this is what we want to improve. So how can we frame the problem, the ranking problem, such that we can affect those metrics, such that we can improve that? So here's how we might want to look at a session. So in a session, we saw you have a list of restaurants, right? And this can be hundreds of restaurants, right? If you're in an area with densely packed restaurants in a big city like London, you're going to see hundreds of those. And This converted is basically, did you order or not? So where we got a 0, a user did not order from that restaurant, and where there's a 1, a user did order from the restaurant, right? So it's kind of like a target variable, right? And that's just one session. But we can have a different user at a different location, and they can open the app as well, and that's a second session. And so for our training data, we take thousands upon thousands of these sessions, and that's essentially what we're looking at. And this forms our target variable. So we decided to frame this ranking problem as a classification, in a classification framework, in a point-wise approach. I'm going to explain what that means. Why can we frame this as a classification problem? Well, what we can do is we can say, ask for each restaurant in that list, we can say, what is the probability that the user will purchase from that restaurant? So that's independent of it on any other restaurants in that list. We just look at that restaurant. That's what I mean by point-wise, right? And classification, because we've saw that the target variable is either 0 or 1. Did you buy from it or not? And then we can then run for a model, and I'll talk about that in a bit, and it will output a score, some probability, and then we just rank in descending order, and that is the rank that's most relevant to the user. Right, so that's how we're going to frame the problem. But it means that because we're looking at this in a point-wise classification fashion, that means we can use a loss function, we can use a logarithmic loss function, right? Just as we would do in any other standard classification problem. And so this is how we're enabled to now train models to tackle our ranking problem, but in a classification framework. So I've discussed the target variable and how we might train models, but we need some features to go into that. So we might want to look at all the different factors that might encourage a user to actually purchase from a restaurant. So it might be the popularity of the restaurant. It might be that if users will purchase from more popular restaurants, or the estimated time of arrival. Perhaps a user really needs some food within 20 minutes. So if there's a 45-minute wait, that's not suitable for them. And perhaps they look at restaurant rating, and there's loads of different factors, right? And we can stick them into some box, run it through F, this box, and output some probability score, right? And then rank in descending order. But F can be as complicated as we want, right? It can be a simple heuristic, or it can be a crazy, dense neural network, or whatever it is. But at Deliveroo, we have this approach that we want to start simple and then just iterate and improve on things. So actually, what we initially began with was just a simple heuristic. F was not a machine learning model. It's just a mixture between the popularity rank and the estimated time of arrival rank. And one of the reasons why would we do this, right? So it's simple, it's intuitive, we can interpret the results much easier, but also we have to serve these results. We have to build an entire infrastructure to be able to serve these recommendations, this ranking of lists, right? So with a whole bunch of moving parts, there's a lot that can go wrong. And we want to make sure we minimize the amount that can go wrong. And so we don't need to concentrate on the complexity of the model while we build out an infrastructure, right? So we started with a simple heuristic that was good enough to get started, focus on getting an end-to-end pipeline and the infrastructure sorted, and then we can start moving on to more complex models. So then we started moving on to logistic regression models, and we're looking at also more complex neural network architectures, and I'll go over some of that a bit later. So, where have we got to? We've discussed the target variable, we've discussed the features, and potentially models that we'll use, right? So we saw that we can get scores, just rank in descending order, and Bob's your uncle, we have a list, right? Is that list any good? We have to evaluate that. Now, we've framed this as a classification problem. So in theory, we could probably use evaluation metrics like accuracy or precision, but when we think about the user experience, they're not looking at a single restaurant, they are looking at an entire list. So actually, we decided it would make more sense to look at an information retrieval metric for ranking, which actually tries to take into account the list itself. And importantly, so that's one reason we're looking at information retrieval metrics. The other thing is, remember that I said at the beginning, we wanted to look at increasing the online metrics, the session level conversion and the order volume. Now, it's very difficult to go back in training data, practically impossible, to then say, if a user didn't order in a session, now I run for my model then re-ranks that list, now they're going to order. It's very difficult, almost impossible to predict that. So offline, when we're training ranking models, we don't evaluate on those online metrics. We need offline metrics, which are proxies for the online. So these methods here are just proxies, and if we improve these metrics, we believe we're going to increase the online metrics. So that's the reason why we're looking at these ones. And so there's a few different ones. I won't go through all of them, but the one that we decided to go for is this mean reciprocal rank. And I'll explain that what it is in a second. But we went for it because it was fairly simple, intuitive, and again, we believe it would be a suitable proxy for improving the online metrics. So how would we calculate mean reciprocal rank for those that don't have much experience in this? Let's suppose we have 5 sessions, right? And on the far left, that's our first session. It's got 5 restaurants, and the user converts or orders from the restaurant in the 4th position, right? The reciprocal rank of that would be 1/4, right? So in the second session, they order from the restaurant in the 3rd position. The reciprocal rank, 1/3, right? So we can do that, and we can do that for all of the other sessions that we train on. And then finally, the mean reciprocal rank is then just the mean of those numbers. Right, so then we get the final fraction, final score, and here it's roughly 0.27. Right? So that would be how we calculate the mean reciprocal rank over all the sessions that we train over in our training data. And we put it in through our test data as well. Note importantly that the mean reciprocal rank has a maximum score of 1. And that corresponds to if we manage to rearrange the list, permute the list in such a way that the restaurant that the user ordered from was always placed at the top position. And the idea is that if we're able to write an algorithm that ranks the restaurant that the user converts from at the top of the list, then it's likely that we're doing a good job with the rest of the list. Right? So, and we'll come back to this. We'll come back to this assumption. Right? Lessons learned. Come back to this assumption. But that's exactly what we've done. That's what we're doing from this point in time. So I've mentioned about the features, the target variable, the evaluation. How does this actually work in our workflow? What do we actually do? So like many of you who may be working on machine learning models, we need to build the train and test sets. We've got a bunch of SQL that does that, queries from our data warehouse, and we can build our train and test sets. Then we have a bit of Python to go and validate that data. So we just want to make sure how many nulls are there. Should there be nulls there? Do we need to impute? What duplicates are there? Things like that. So we're just trying to validate that. Then we get into training. And so notice we're going to train on this validated data. And we train loads of different models. And the difference between model 1 and model 2 can just be a removal of one feature. It can be a completely different model. It can be a heuristic. It can be a logistic regression. But we train several different models. And each of those models will have its own permutation of the list. So with a different permutation, I can calculate a mean reciprocal rank for each one. And then, as I said before, we just choose the one that gives us the highest score. Right? Come back to that. But we choose the one that gives us the highest score, and that's the best model. And once we've chosen that, we can then put all of that into production. Right? So we use a continuous integration tool called Circle CI that will run a whole bunch of unit tests for us, and then push some Docker images, I should say, up to Amazon S3. And then we have an inbuilt machine learning pipeline called Canoe, which basically runs this job periodically each day. And so that's how we then do that. So at that point, we've built some models, we've evaluated them offline, right? And we've productionized it. Great, we're in a good position. But the thing is, we have not checked that it's moved our online metrics. We've not checked that it's moved the things that we believe achieves our objective. Right? So to do that, we need to run this online. We need to run it. We need to run an A/B test. So what we do is we run a user-level randomization. So a user will get a version of the model. So 50% will get the current version. Another 50% will get the new proposed model. And we'll run the A/B test, look at those online metrics, and see which one actually gives us an increase in those metrics. And we'll choose that one. Right? But this is an iterative process. So I said at first we started with a simple heuristic model, for example. That might have been a good start, but then we do a slightly more complex model, and that might win. But then that's still not an optimal model. So then we build an even more complex and better ranking algorithm. So this is a process that we go through over and over again. So we run multiple A/B tests to try and improve our rankings. So, and we're at the point now, so that's the whole pipeline of what we do and how we work. And our approach to the problem. And at the moment, we're in the process of building slightly more complex models and feature engineering. So as I said, we've been using a lot of logistic regression at the moment. We're currently working through wide and deep neural nets as more complex models, but also more feature engineering. So looking at new features, but also embeddings of features. Like, can we get better representations of the features that we're already using to improve our search results? So we still believe that there's a lot more that we can do to improve the rankings that we actually show. So that concludes the approach to the ranking problem. But as I said, we need to build an infrastructure that enables us to do this. So I've mentioned a lot of the data science work, but what about the infrastructure that supports this? So, you know, we're in this in a situation where actually we need to build something that can serve features that sometimes are aggregated and we can get daily or in advance. So we can write some SQL to get sort of like past order volumes and things like that, past conversion scores. But then there are some features that we don't know until serve time. So the estimated time of arrival, we can't know prior to the user actually starting the session and opening the app. So there are these things that we have to consider when we build an infrastructure to serve this. So we considered several different ways that we could productionize our models. One of the things that we've done historically in Deliveroo, and one of the things we considered, is let's say that we write our model and our team writes the models and does all the analysis in Python. We write a model, we've chosen it, it gives us the best mean reciprocal rank score, and then we say, okay, let's go and sit down with an engineer and rewrite that model in the production language. And then the production language now has a version of that model in there, and that can just serve straight from there. And that's what we've done in the past. But as you can probably imagine, it's a bit slow. It's a time-consuming process. It's prone to errors, right, if we get the mistake in copying the model over. But also, it limits the complexities of the models that we can actually use. All right, because we have to implement it all from scratch. So we'd have to implement like tree-based or neural networks from scratch in Go if there wasn't a library for it. So we decided to think, OK, what's another method that we can use to productionize? Well, what about if we didn't need to rewrite the model in the production language, but instead we wrote a model in Python and then just containerized it and released it as a separate microservice. So now the actual production service that shows you and renders the home page would call out to this Python microservice, and then via some maybe HTTP interface, and then the microservice would go rank restaurants and return it to the production service, say, hey, here's a ranked list of restaurants. So that's cool, but remember that actually you don't want to wait a long time when you open the app, and we were worried about potential latency problems in making a lot of requests over the network, and also at busy times where there's a lot of requests, we might need to scale some containers up and down, and actually figuring out what to scale and when to scale was going to be slightly difficult. So we went with option 3, which is basically to integrate a serialized version of the model into the production language. So what do I mean by that? So we can serialize Python objects. So when you save a Python object, we usually use pickle. And then you can read that back, and then you can use the variable again. The problem is pickle can only be read in Python, and our production language is in Go. So what about if we serialized in a format that could be read from different languages? And so we figured, well, this is the case. Let's try and use a framework that would enable us to do that, and which is why we chose to implement our models in TensorFlow. That is the main reason, because it allows us to serialize models in a format in which we can read from other production languages. But there are also other benefits to TensorFlow. One, it's fairly mature. So it's got a good community, it's got good documentation, and so we could guarantee that there was going to be a good level of support when we got stuck. It includes a whole range of models. So you can implement linear models in there, trees via the contrib module, but also deep neural nets, and it isn't much of an API change. And because we're more familiar with linear models, we were very interested in using something that could serve linear models, but also enable us to easily go more complex. And also, it has this, what's called the estimator API. I want to explain that because I wasn't familiar with it until we started looking into TensorFlow. But basically, the idea is to give an interface that allows you to write models similar in fashion to how you would in scikit-learn. So I don't usually like putting code up on screen. I promise I don't. But I don't need you to focus on the code. I just want you to focus on what bits this is. So this is an example of how the TensorFlow estimator API might work. So basically, the first thing you need to do is define how the data needs to flow into the model. So if I have let's say a CSV or a pandas data frame of the data, I need to say, oh, I want 1,000 observations to go in each batch. I want to shuffle that batch because I want to randomize the data and all that. So we write a function. I haven't put it in there because I couldn't be bothered, and I want it to fit on the screen. We then need to create features. So TensorFlow needs to know whether a feature is numeric, because it might want to scale it, or if it's categorical, because it might want to do one-hot encodings or embeddings. But the last two bits are what make the estimator API familiar to us. So if I want to use a logistic regression classifier, I just do tf.estimator.linearClassifier, right? In a similar fashion to scikit-learn, right? And then again, if I want to train it, I can now do classifier.train, right? Which is analogous to classifier.fit in scikit-learn. And importantly, if you have used low-level TensorFlow before, and you've remembered that creating placeholder variables, you can run multiple sessions, and it's just a headache. You don't need that in your life, right? So this enables us to not worry about any of that stuff. It doesn't, we don't have to worry about creating those variables, and we can train models in a simple fashion. And if I want to switch to a deep neural net in the estimator API, I can change linear classifier to DNN classifier, for example, and just add a few more arguments. So now we can change to more complex models in a very, very simple way. And then importantly, the other important thing to remember is that we need to write inference in Go. Are there any Go writers in the Go writers in the audience? Okay, a few. I've tried here. I don't write Go. I've tried. But this is roughly how it would be done, right? Roughly how it would be done. So you import the TensorFlow module in Go. You can write a function, get model. It just needs to download the serialized model that comes out. But importantly here, so model.session.run. So it's a similar interface in another language. And then it takes as the first input the feed dict for anyone that's familiar with TensorFlow. We put in the input features, and then the next argument is the fetches. So the node in the TensorFlow graph that says, OK, I actually want to get the probabilities from the logistic regression classifier. So that's the output node. And then you got your results. That's how we do inference. It's great. It's great. So this is how we actually read from the serialized model in Go. So at the start of this section, I was talking about the different approaches to productionizing the model, like the different considerations. And one thing we're looking into is how something like Amazon SageMaker can help us improve that flow, because there's still a bit of friction in doing that. There's still a few hoops. And hopefully, we can use this tool to help out with that. But additionally, SageMaker, even if it doesn't change things on the production world, it helps with parallelizing model training and also hyperparameter optimization. So we're looking at using this for several different parts of our workflow. So yeah, we're in the early stages of that, but AWS has been very helpful so far. Cool. All right. So we looked at the approach to modeling, right? Ranking, we've discussed how we train, evaluate, and then also the tools, how we built the infrastructure to do this. And we've deployed several models, we've run several A/B tests, and we've made several mistakes. And so I just want to devote the last section of this talk to some of the lessons that we've learned. And if there's anything that you take away, I hope that these are going to be able to help you in some of your projects as we go forward. So the first one is, even though you productionize your model, you serialize a model, and everything works in your training environment, you also have to serve this. And actually, when you serve it, there may be bugs in a data science code. There may be bugs in the engineering code. And so you can actually get different results, different ranks in production to your ranks in training, and you won't know it. And when we started, sometimes we didn't actually check this at first. And when we were starting to see different ranks and different results, we're like, what's going on? Something simple we can do is just check the train serve skew. Check that production actually matches what you expect in your training environment. So this is, I showed you one here that's perfect. We check the ranks on production versus offline. I don't write bugs in code, so this is perfect. If they all land on y equals x, then we have perfect ranks. Our production ranks match training, right? But actually, if we see a scatter here, that means something's gone wrong, right? So something's different. So then we also have to check the features. So for example, if I go onto my phone and we serve a ranked list, I can see an estimated time of arrival of, let's say, 20 minutes. All right? That's what a user will see. And then the next day, that goes into a warehouse. And I can write SQL to generate a data set. So now my SQL gets the estimated time of arrival for that same user and session, and it might not be 20 minutes. And so we want to check that when we write our SQL for our training data, it actually matches the inputs that are going in production. And so here is what we can see, like 4 features here that did not match what we saw in production, and the proportion of times that it did not match. And so looking at these things can really help actually find bugs. Sometimes it may not be in the code that you've written. More often it's in my code. But sometimes it can be in engineering code as well. And this can help find where those problems might be, and we can fix them. So doing this every time and setting it up so it's actually part of the pipeline can be very, very time efficient. I'll come back to that later. Log and monitor everything, right? So if there's a number you know you need, log it. If you're not sure, log it. If you collect the number and you don't think you need it, log it, right? I promise you, it's just so important. So like the example I'm just going to use to explain this. So we have to write SQL to get the sessions get session data so we can train models, right? And that runs every day. And over the last few months, Deliveroo has started to revamp and change the back end to the home page. And so it meant that the tracking changed. And we didn't log this. And so for a week, we were starting to miss data because the SQL columns weren't matching. They were all nulls. We didn't log this. We didn't really look at it. And what we then saw was at the point at which the training data period was completely messed up, that's when we got an error saying our model didn't train today. It turned out this was actually a problem for quite a while, and we just weren't seeing it. And so we actually then had to go back. But the only thing is, all you've got is your logs. That's all you've got. So we have to start from the training script, where actually we just saw the model didn't train, but actually the problem was way back. Our SQL wasn't collecting the data, so it was a few scripts down, and it actually wasn't a change that we'd made. It was a change on the back end from the engineers. We didn't actually change any of our code, but things went wrong. And if we had logged everything and we'd monitored everything, we would have caught it much earlier. So if there's numbers that you're not sure that you need, just get them down. Just get them down. It can save you a whole bunch of time. And here's one I'm going to come back to. So I mentioned to you that we ran many models, calculated mean reciprocal ranks, and we said the best one was the one that gave us the highest score. That's actually not always true, and it can be very misleading. In fact, there were times where we saw in A/B tests that we'd released a model that increased the mean reciprocal rank, but none of our online metrics actually changed, right? And this has led us to start to conclude, what are the limitations of mean reciprocal rank? Well, actually, it only assesses the single session that was converted. It says nothing about the rest of the restaurants in that list, right? We made an assumption that if we could put one restaurant at the top, we were doing well with the other restaurants, right? That assumption fell through, right? And so actually, we figured we needed to start to look at several different metrics. So there's no one single metric that we're looking at anymore. So one of the things we go and do is we look at, again, scatter plots. So let's look at what are the ranks of the current algorithm versus the ranking of a new proposed algorithm, right? If they lie on the line y equals x and they're completely identical, well, then if you release an A/B test, you're not going to see any changes because the ranks are identical. And so actually, we can tell by how much scatter is in these plots, and we can quantify it with the Spearman's rank correlation coefficient, like how different ranks of models are. So now we can actually start to determine in advance how different, what differences we might expect in an A/B test. The other thing that we find incredibly useful is actually looking at the surface you're changing. So we're actually changing the ranks. When we release this model, what do users see? What is their experience? They see a rank of restaurants. So looking at a global metric, you're not actually looking at what the customer experiences. And so actually what we end up doing, some of the engineers in our team built this ranking insights visualizer, and we've released it to all employees, is that we can actually, it's not very clear on there, but you can like switch between different models that we have in production and actually look at what ranks you'd expect. And you can put in different locations, different postcodes to see where the ranks make sense. And this is incredibly important because if I now look at this and I can see at dinner time, I'm getting breakfast restaurants at the top of the list, maybe I haven't accounted for time properly in the model. So looking at things like this can help us really understand the changes that we need to make in the model to improve our recommendations, our rankings. So it's just something that we use as a sense check. And finally, if you've not read Google's rules of machine learning online, go and read them. And if you've read them once before, read them again. Like, I find it incredibly useful, actually not just me, but like other members in the team, to go back to this, like, 2 months down the line, 3 months, because actually some of the rules make so much more sense after you've seen them and you've gone through the issues, and you're like, actually, if I'd just done that earlier, I would have caught the problem. And so, yeah, go back and read that. So in summary of the lessons learned, check the differences between training and production environments, right? It will ultimately speed things up. And we can actually check that we're making the impact that we want, right? If we can check that our models are working accurately, then they'll have the impact on the metrics that we want. The other thing, log and monitor all the things, everything. It's so useful. Don't just rely on global metrics as well, right? So global metrics are fantastic, they're good. Regression, use RMSE or whatever, use accuracy, whatever you want, but don't just rely on them. Actually look at some of the predictions themselves. Make sure that the predictions you're making make sense. And finally, read Google's rules of machine learning. So yeah, just to wrap up and rehash everything I've just said. So in the team, we had an initial aim to like improve the restaurant ranking, and we wanted to improve the relevance of the restaurants to the consumers. And we built an infrastructure to do that, and we've built a bunch of models, and along the way, we've made mistakes, and we've learned so much from it. And there's still more to learn. I'm sure there's going to be a lot more pitfalls that maybe next year I'll come back and talk about a few more, who knows. But we've actually got work to do because we're trying to expand what we're doing. So that's just ranking of the restaurant list, but there are other things that we want to do. Ultimately, we want to algorithmically design and create the best experience for the consumer. We might want to touch different services, so we need to look at search results and filter, and horizontal scrolling carousels you might see, like, oh, order again, or there's some discounts and stuff like that. So we actually want to try and start to do algorithms that will affect the whole experience. But that's not all we do. You can probably tell now that I'm starting to get to the promoting Deliveroo here. That's not all we do, I'll have you know. There are other algorithm teams, right? We need to work out how much should like fees, right? How should we set them? We've got a network, and the network's different in different places, and we order from different places which are further away. Should it change? Thank you. Logistics. I've mentioned at the start, we have a three-sided marketplace with a ton of restaurants and riders and consumers, and they're everywhere. How can we make sure that this network runs efficiently? There's a lot of complicated problems there. And also, we run a whole bunch of A/B tests, whole bunch of experiments. I'm not first to finish. We run a whole bunch of experiments. And so actually, it's we want to try and standardize this process and get out there. So we're building an experimentation platform. So come and help us do this. And obviously, guys, we're hiring. Join us. We're at our stand at the entrance to the big room at the back. I'm going to be there after this talk and to the end of the day. And there'll be at least one data scientist and a recruiter on there all day today and tomorrow as well. So come see us. And finally, thank you for listening.
Do you have any questions?
Epic talk.
Thanks, man.
So I've also done some recommenders, and I've also sort of noticed that like there's these proxies, and they don't necessarily correlate with real life. Have you found any proxies that do?
So not perfect. And actually, I've been trying to read like quite a few different recommendation articles and papers to see if there are like good offline metrics that better represent online. I haven't seen any. One of the things that we've done in our team, but we just need to do a few more experiments, is we're trying to actually correlate offline metrics with what results we get in experiments. And so because we're running experiments, we do have online data points, but obviously each experiment on its own is one data point. And so we need to run quite a few to build that correlation. We can calculate things like online mean reciprocal rank, online precision at K. But yeah, the short answer is we haven't yet found it, but I think the work we'll do in correlating those will hopefully help, but it's not perfect.
Anyone else? I think.
No hard questions.
Thanks for the great talk. I'm glad that you said that MRR has limitations, and really happy that you had that on your slides. So I had a comment and a question. So the comment is MRR is hard to interpret because, for example, the difference between putting the relevant restaurant in rank 1 and rank 2 is exactly the same as putting the relevant restaurant in rank 2 and rank infinity. So I wonder if you see interesting patterns in the data, similar to what I described. And also, if you're going to use precision at K, for example, what value of K would you use in your case?
All right, so first question, mean reciprocal rank, do we see? So as you can imagine, with it being reciprocal, if you place the restaurant at position 1, you get a mean reciprocal score of 1. If you place it at position 2, it's now half. But if I place it at position 3, it's 0.33. So the difference is, although we're still moving the restaurant in the same amount, the differences between the scores change, right? So it's not perfect. How do we account for this? I personally, and this is a thing, so I think like evaluating these recommendation systems and ranking systems are, in my opinion, is quite subjective. I like to think of the mean reciprocal rank as thinking about it as almost like a threshold. Like, if you can get a mean reciprocal rank, which is a 0.2, that means on average you're placing the restaurant in the 5th position, right? So you're doing fairly good there. But once you get to that point, I think if you start getting ones that are lower, maybe that's not good enough. And so actually, once I start getting mean reciprocal ranks of more than 0.2, I'm starting to think that there's not much difference in the ranks. And actually, what's more important is looking at the ranks that are individually set for me, looking at the scatters, and starting to assess whether actually it looks like it's learned something. Because now I can see that breakfast time, I'm seeing a whole bunch of breakfast restaurants. It's not perfect. But we've not settled on any good way to rank that. Precision at K, this was some of the work when we were correlating the online metrics with the offline. We found that 30 seemed to be best for the data points we had, but I don't think I had enough data points to be able to say that firmly. So no one quote me saying 30 is the best, but that's what it looked like. But for me, intuitively, I think 30 would be too much. I actually think we'd want to set it lower, because I think when you think, like, just think about having a session, how many restaurants do you scroll through before you evaluate whether a list is any good? Do I need to evaluate through all 30? So do users do that? I actually don't know. And we're like implementing scroll tracking to start to see what they're seeing. But yeah, it's hard to know at the moment. So yeah, I couldn't answer that problem.
Okay, I think
You mentioned that it's a marketplace of three parties, but your goal is very focused on one. Do you have any thoughts about how you would extend the work you've done to maybe it might be something that's taken in how it benefits the riders or new restaurants, et cetera?
Yeah, so I'll try and be relatively quick because I know we're running out of time. Yes, it only focuses on one, and actually the change that we've got to make is in the objective function. I read a paper very recently by Spotify. It's called Towards a Fair Marketplace. Read it if you're doing any ranking problems. They're looking at relevance to the user, fairness to the artists, so that would be like fairness to the restaurants around us, and actually what is satisfaction for the user, and can they balance fairness and relevance to get the best satisfaction. I think that we can change the objective function so that we can like show users more restaurants that are of a wider variety, but we're still early days and we haven't got to that point. But yeah, we can.
Great. Let's thank Jonny one more time for a great talk. Thank you.